Hello everyone, Assalamualaikum warahmatullahi wabarakatuh, and good day to every one of you. Welcome to my video. So basically in this video we are going to continue our lecture session for chapter 2 which is power in AC circuit. Alright, so here is my name and this is my email address. So you can just feel free to email me whenever you have a question regarding the content of this video. Right. So for the contents that we are going to cover in this video, basically is the first subtopic is the power in AC circuit, and then after that we are going to see the definition on the power factor. Okay, alright, so for the power in AC circuit, we are going to see the various type power that available in the AC circuit, which is active power, reactive power, and also the apparent power. Right. So we go to the first subtopics, which is the power in AC circuit. So the behavior of the AC machines and system are often easier to understand by working with power rather than working with the voltage and current. Okay. So the active, reactive, and also the apparent power apply to the steady state AC circuit with sinusoidal waveform only, right? And it cannot be used to describe the transient behavior, and also cannot be used to describe the DC circuit. Okay, alright, so the instantaneous power in the AC circuit, okay, is a product of the instantaneous voltage multiplied with instantaneous current, and then the unit of the instantaneous power in AC circuit is in watts. Okay, so usually the P will be given by IV. Alright. Okay, now let's have a look at the first type of AC power, which is active power. Okay, or we can also write it in terms of P. Alright, so the diagram here shows you the AC power waveform for a pure resistive load. Okay, so the keyword here is a pure resistive load. When your AC circuit is contain only resistor, so that your voltage and current is in phase. Okay, so V is represented by your blue line, blue solid line, and I is represented by your red solid line. Okay, so the multiplication of the V and I is equal to P. Okay, power will be equal to V multiplied with I. Okay, alright. And then the average value of the instantaneous power over one cycle of the voltage is considered as the active power. Okay, so the active power, also known as a real power, or we can also call it as a true power or actual power. So the active power is actually the effective power that does the real work. So the unit of the active power is in watts. Okay, so it's given by P equal to IV cos theta, where the theta is the angle between V and I. Okay, so P will be equal to IV cos theta. Right. Since you know that V will be equal to Iz, so P can also be written as, so here the V, you substitute with Iz. Okay, so I multiply with Iz, so you got P equal to I squared Z cos theta. Alright. Okay, so this is for the active power. So next, let's have a look at the second type of the AC power, which is reactive power, or the symbol used is a Q. Okay, so the first diagram show you the AC power waveform for a pure inductive load. So for a case of inductive load, you know that your AC circuit only involve an inductor. Alright. Okay, so for a case of the AC circuit that involve the inductor, you know that the voltage will be lagging the current. Okay, so or otherwise current is leading the voltage. Okay, and then the multiplication of the V and I will be equal to your P here. Alright. Okay, so the reactive power is also called as a circulating power in the circuit. Okay, so meaning that it does not do the real work. Okay, so if you have a look at here, you know that P will be equal to I multiplied with V. Okay, so for this side, okay, if you multiply with this side, you can get the purple color here. Okay, so if you refer to here, the positive cycle will represent the power consumed by the AC circuit. Okay, and then the negative cycle represent the power return to the AC circuit. Okay, so that's why we call it as a circulating power. Okay, the power will be circulate. Alright, and then it is also known as an imaginary power, and it does not do any real work because it will cancel to each other. Okay, so the unit of the reactive power is in volt ampere reactive, or we can also call it as a VAR. Okay, alright. For a case of AC power waveform for a pure capacitive load, okay, so same goes as per above. Okay, it also have a power consumed at the positive cycle and power return at the negative cycle. Okay, remember for the capacitive load, you know that your current is leading your voltage. Okay, alright. And mathematically, the Q is given by IV sine theta, where the theta is the angle between V and I. Alright, and then you also know that the V will be equal to Iz. Okay, so we can substitute this into the equation here. So you know IV will be equal to I multiplied with Iz. So finally Q can be also be written as I squared Z sine theta. Alright, so that's for the reactive power Q. So next we go to the complex power S. So the complex power is actually the product of the voltage across the load and the current through the load. Okay, so V voltage multiplied with I. So that's why the unit is in volt ampere, VA. Alright, and the apparent power is actually the absolute value of complex power. Okay, so meaning that now your apparent power S will be equal to the amplitude of the complex power. Okay, and then the apparent power will be equal to IV. Alright, so since you know V equal to Iz, so this is from the Ohm's law, we can just substitute this equation into here. So S, the apparent power, can also be written as I squared Z. Alright, so that is for the complex power. So next we are going to see the concept of the power triangle. So the power triangle essentially give you a relationship between S, P and Q. Okay, so in order to understand the relationship between these three, we can represent graphically by using the power triangle. So this is the power triangle where you have a P at your real side. Okay, and then for the imaginary side you have Q, because you know Q is the imaginary power, right? So this is your real power here. Okay, and then here you have the apparent power S. Okay, so by applying the trigonometry, you know that S squared equal to P squared plus Q squared. Okay, alright. So for the inductive load, so you know that for inductive load where your circuit only have a combination of resistor and inductor, so your theta will be larger than 0. So in this case, theta V is larger than theta I. So theta is larger than 0. Okay, so in this case, it is here. Alright, so Q will be equal to IV sin positive theta. Okay, because positive theta larger than 0. So in this case, we consider as a positive Q. Okay, so for the positive Q, positive side here, alright, so we can consider it as a lagging power factor. Okay, for a capacitive load, you know that your theta is less than 0, meaning that your theta V is smaller than theta I. Okay, when the smaller number minus the larger number, so you get negative number less than 0. So in this case, so your angle is negative. So that's why you are getting negative Q. Okay, so you are having the capacitive load at this region. So it is negative Q. So in this case, we consider as a leading power factor. Alright. Okay. So next, this is the summary that we made based on the discussion earlier. So basically, load have three different type, where you have a resistive load, inductive load, and capacitive load. For the resistive load first, so you know that I is in phase with V, alright, and then theta will be equal to 0 because the theta of the V will be equal to the theta of I, so that's why theta is 0. So in this case, your Q is 0. And the power factor is unity because power factor is cos theta, cos 0. Cos 0 is 1. So 1 is considered as a unity power factor. For the second load, which is inductive load, you know that the I will be lagging the voltage. Okay, because for inductive load, the inductor will be induce the magnetic inside the inductor itself, and then it will cause the current to move slower than the voltage. So that's why I lagging the voltage. Okay, so for the theta, because I will be lagging than voltage, so the theta I will be smaller than theta V. So that's why theta V minus theta I is larger than 0. So it is a positive number. So that's why Q is positive. Okay, so in this case, power factor is considered lagging because current lagging voltage. So power factor is lagging. Alright, so the last type of the AC load is a capacitive load. So in this case, I leading the voltage, right? So you know that for the theta will be theta V minus theta I. So in this case, I leads the voltage. So the theta I will be theta I is greater than theta V. So that's why you are getting negative number here. It's less than 0. So when negative number, Q is negative. Alright, so in this case, power factor is leading. So why leading? Because current leading voltage. So power factor is leading. Alright, so here current lagging voltage. So power factor is lagging. Alright, so that's how you remember. Alright, okay. So now let's have a look at the following example on how to use the power triangle. Alright, so the question here, an equipment draws from the supply system a 1000 kVA load with a 0.8 power factor lagging. Okay, and then you need to find the real and reactive power of the system. Okay, so the solution to the example, first of all, we write down all the information given. So from the question, you know that S, the apparent power, is equal to 1000 kVA. And then you also know that the power factor is 0.8 lagging. So in this case, when you know that the power factor is lagging, so meaning that it is an inductive load, and then you also have a Q positive. Okay, and then what is the value of P and Q? Okay, alright, so if you refer to here, this is the positive Q, where you have a, you refer to the power triangle, you have a P, Q, and S. Okay, alright, so from here, you know that when you have a theta here, cos theta will be equal to P divided by S. Okay, so this is based on the trigonometry rule. Cos theta will be equal to P divided by S. So cos theta is equal to power factor P divided by S. And then you know the value of S, and then cos theta also given from the question. Then you can find the value of P. So P is equal to S cos theta. So you just substitute the value. S is 1000K multiplied with cos theta is 0.8. So finally you get P equal to 800 kilowatt. Right? And then you also know that based on the trigonometry rule, S squared will be equal to P squared plus Q squared. We can rearrange the equation so that you have Q is equal square root S squared minus P squared. Okay, and then we can just substitute the value of S from here, P from here. So 1000K squared minus 800K squared, and then we find the square root value of the operation. And then finally, you get 600K VAR. Okay? Alright. So that's how you apply the concept of power triangle in order to solve the problem. Okay? And then we go to the second subtopics, which is power factor. So what is actually the concept of power factor? Power factor indicates how effectively electrical power is being used. And then the value of the power factor can be in range within 0 to 1. Okay, so it can be computed as follows. So usually the power factor, based on the power triangle, you can use the formula of active power divided by active power P divided to the apparent power S. So power factor is equal to P divided by S. Okay, so this is based from your power triangle. And then you can also calculate based on the cosine of phase difference between the voltage and current. So the power factor can be also equal to cos theta. Alright, so where your theta is actually theta V minus theta I. Okay, And then for the power factor correction, okay, so this is for your general information. So the power utility will impose a penalty to the industry if the PF is less than 0.85. Okay, because they need to cater for bigger equipment such as transmission line, cable size, transformer. Okay, so that's why usually when the industry, they need to measure the power factor. If the power factor at their side is less than 0.85, usually the power utility will impose a penalty in terms of their bill electricity. Alright, okay, so meaning that they need to pay more to the power utility. Alright, so there is a mitigation technique in order to improve the power factor at the end user. So usually the mitigation technique will be applied at the industry level lah. Alright, so usually they will install the capacitor bank to correct the power factor, meaning that to improve the value of power factor. Okay, so ideal case is 1. Okay, so usually in order to improve the PF to get near to 1, so maybe you are getting 0.9. Okay, so you need to install the capacitor bank at the end user, at the industry level. Okay, so how the capacitor bank works actually, the capacitor will deliver the reactive power to the circuit. So the circuit will not draw the reactive power from the supply. Okay, alright, so that's all for now. Thank you for your time. Thank you for watching my video. I'll see you in my next video. Okay, bye.